Hello everyone, welcome back to the class of the hydrocarbons. In this particular class we are going to discuss about the alkynes, right? So alkynes, these are nothing more than the compounds which are going to contain the carbon-carbon triple bond. At least one carbon-carbon triple bond should be present. So our first observation about these particular set of compounds is that these compound or the molecules should contain at least one carbon-carbon triple bond. Okay, so this is our first observation. Now when we take a particular alkyne and try to compare it with corresponding alkane, okay, alkyne with alkane, what difference I would find is a difference of 4 hydrogen atoms. Alkynes have 4 hydrogen atoms less than the corresponding alkane. Let us try to understand this point. Now if I am going to take over here, let's say for a moment, I am going to take over here C2H6. This is nothing more than CH3 single bond CH3, that is our ethane, right? Now when we compare this particular ethane with the corresponding alkyne of this particular thing can be like C2H2, right? Now C2H2 is nothing more than an ethyne, correct? So when you compare an alkyne with the corresponding alkane, what we find is the difference of 4 hydrogen atoms. That is, I need to say that your alkynes contain 4 hydrogen atoms less than the corresponding alkenes. Okay, so this takes us to its formula. The general formula of this particular alkynes will be as CnH2n minus 2, correct? So this is going to be the general formula of alkynes. Now, speaking about the first stable member of this entire series of alkynes, and that is our ethyne. Now, ethyne has the other name. It is also called as acetylene. Okay, so acetylene is nothing more than ethyne, which contains a carbon-carbon triple bond. Now, this particular compound, this particular molecule, okay, it has a very important role in arc welding. So, this particular compound is used for arc welding. Okay, now in the arc welding, it is used in the form of oxyacetylene. Remember this, very important. Okay, so oxyacetylene is nothing more than a mixture of oxygen and acetylene. Okay, so that particular mixture gives a very high temperature and hence it has been used in the arc welding. Okay, now before going to the reactions, you need to understand how to name them. So let's start to name these particular compounds. Let's go with the basics. Okay, so first, let's take over here the formula, right? Let's take over here its corresponding structure. Over here, we shall discuss its common name, followed by, let's go over here with respect to an IUPAC name. Okay, I hope it will do good. Now, the first one, let's discuss the first one, which we have already looked at it, that is C2H2. Alright, when I take a look into its structure, it is going to be as CH over here, triple bond CH here. Okay, the common name we have already discussed for this C2H2, and that is our acetylene. Correct. While we take a look into its IPAC naming, we have already known that also. That is nothing more than ethyne. Okay, so this was the first one, quite easy. Okay, now when we go for the next molecule, okay, that is C3H4. Please observe it now. Okay, so when we take a look at its structure, it's going to be as CH3, C triple bond CH. Okay, so we have 4 hydrogens, 3 carbons, 3 carbons. Correct. Now, IPAC name. First, let's discuss the IPAC name. 1, 2, 3. 3 carbons, so therefore it becomes as prop series. So prop, right? We have a triple bond, so it will become as propyne. Okay, now here this structure and this structure is almost same this side. Correct. What we have extra is this. This particular group over here, we will consider it as methyl. So it becomes as methyl, this section. Okay, and this section is your acetylene. Right? So we will call it as a methyl acetylene, common name. Okay. Now we'll go one step further. Now over here, let's say we have C4H6. Okay. So let us take the same way, that is CH3, CH over here, C triple bond CH over here. Okay. So it is going to be as CH3, CH2. So this is the entire thing. Okay. So let's consider its IPAC name. So when we consider the IPAC name, like 1, 2, 3, 4, right? 4 carbons. So it will become as butene series. So but 1YNE, butane, right? So but 1YNE, right? So now when you take a look into its common name, okay, so what we have, again, this you consider it as an acetylene section this side, and here this is an ethyl. Okay, so it will become as ethyl acetylene. Okay, so ethyl acetylene. Now observe this carefully. We can have another way for C4H6, and that is going to be as, observe carefully, it is going to be CH3, okay, C triple bond CH3, right? Now, does it hold this particular formula good? Let's check it out. So here, 3 hydrogens, 6 hydrogens, 1, 2, 3, 4, 4 carbons, done, perfect. Okay, so here, the IPAC name changes as 1, 2. At the position 2, you have now a triple bond. So it becomes as but. But refers to 4 carbons. So 1, 2, 3, 4. Right. So at the second carbon, you have a triple bond. So therefore, we'll write it over here as 2YNE. Butane. Right. Now, the common name for this. So when we have the common name, please observe, this is your acetylene group. Okay, the central one. Now here you have a methylene, here you have a methylene. Okay, so this common name becomes as dimethylene or dimethyl acetylene, right? So this is how we get it. Okay, so this was an ethyl acetylene, this one will be a dimethyl acetylene. Okay, so these are the common names. Now here, the thing that we need to note is between these two. Please observe CH3, CH2, C triple bond CH. Okay, so this is one CH3, C triple bond C, CH3. This is the second one. Okay, now the main difference between these two, of course, both of them have the same molecular formula. The main difference between these two is with respect to the position of that particular triple bond. In the first case, the position is at the carbon number 1. In the next case, it is at the carbon number 2. Okay, so hence alkynes having more than 4 carbon atoms also exhibit isomerism. So first point for your competitive exams that you have to remember is the alkynes exhibit isomerism provided they have more than 4 carbon atoms in that particular molecule. Okay, so alkynes with more than 4 carbons will exhibit isomerism. Okay, so they are going to exhibit isomerism. Okay, so therefore, can I say that these two are the positional isomer, that is nothing more than but1 and but2, right? So therefore, this one, we end up over here with respect to its nomenclature. Let's now observe about its structures. Now let us understand the structure of these alkynes. Okay, now in order to understand the structure of alkynes, let us take one example, and that particular thing will be your ethynes. So let's understand the structure of alkynes. Okay, by taking an example of ethyne. Okay, so when I am saying an ethyne, we already have seen its molecular formula. So molecular formula right? So now let's take this particular thing. Now try to understand that it has 2 carbon atoms. Now here both the carbon atoms, as what we have, both these carbon atoms are going to be, please observe carefully, very important, both of them are going to be an sp hybridized. Okay, so what we have over here, both of the carbons are sp hybridized. So how many orbitals are we hybridizing? We have one s orbital and we are hybridizing one p orbital, correct? So when we hybridize these things, we are ending up getting over here an sp hybridized carbon atom. Both of them are going to be sp hybridized. So out of 2 sp hybridized orbitals, so it will give rise to 2 sp hybridized orbitals. Okay. So what is going to happen over here is that one sp hybridized orbital, it is going to give rise to 2, right? So for one carbon, it is going to give rise to 2 hybridized, that is sp hybridized orbital. So therefore, out of 2 sp hybridized orbital, both these carbon atoms, they are going to use 1 in order to overlap. With the s orbital of hydrogen. Remember this. So this is your hydrogen, this is the carbon, right? So what is going to happen over here? This is the hybridization. Okay, that is the sp hybridization, which is overlapping with the s orbital of hydrogen, giving rise to sigma bond. Same thing happens over here. What is happening? One sp hybridized orbital, this is your sp hybridized orbital, correct? It overlaps with the s orbital of hydrogen. So this is the s orbital of hydrogen, giving rise to sigma bond. Okay, so sigma bonds are formed. Okay, so I'll draw this complementary structure here as HCCH. This is what it is giving me, correct? Now, what happens is both of them still have one sp hybridized orbital. Okay, so now these sp hybridized orbitals, sp hybridized and this one is sp hybridized, correct? Now these two are going to get overlap in order to give another sigma bond over here. So here is another sigma bond. So this is sigma, this is sigma, and of course this over here is a sigma bond. Okay, now usually a carbon has 1 s orbitals and 3 p orbitals. Okay, so usually one carbon atom has 1 s orbitals and it has 3 p orbitals. Correct. Now, what has happened over here? You have taken 1 s and only 1 p for the consideration. How many are remaining with you are the 2 p orbitals for each carbon atoms. Okay, so one carbon has used 1 s and 1 p. So what remains is 2 p orbitals with it. So therefore, what is going to happen here is this carbon, which is already forming 1 sigma bond over here, 1 sigma bond with the next carbon over here. Okay, now it has an unhybridized orbital. Okay, now let's say these are unhybridized px orbital. Okay, so let's take over here. These are your 2px. This is over here 2px. So same thing over here. This is 2px and this is of course 2px. Right? Now, it has one more orbital. Which one it is? It's going to be 2py. Okay. Now, let's consider this 2py over here like this. Okay. Now, please understand this particular px and py are perpendicular. That means the angle between those two is 90 degrees. Okay. So, let's draw over here also. So, this is 2py, this is 2py. Alright, so let's take over here 2py and let's take over here, this is going to be our 2py. Okay, so this is 2py, this is the 2py. Correct. Now, final thing, what is going to happen is that 2px. Okay, now this one is called as the lateral overlapping or the sideways overlapping. Okay, so 2px, they overlap in order to give us 1. What it is giving us? Pi bond. Okay, so this particular overlapping ends up forming 1 pi bond. Okay, on the other hand, these two, observe carefully, now these two here, they overlap, giving rise to the next pi bond. So it will give rise to the next pi bond. Okay, so here actually there is a sigma bond which we have already seen over here. Okay, so 1 sigma bond between the 2 carbon atoms and the 2 pi bonds between the 2 carbon atoms. Correct. So therefore, this is actual structure. Now, if you observe the particular angle, the angle between the hydrogen, carbon and the carbon, this particular angle, hydrogen, carbon, this angle is going to be equal to 180 degrees. So, hence this particular compound, this particular molecule is going to have a linear structure. So, therefore, it is going to give rise to the linear structure. Okay, so this was all about the structure of ethyl. Okay, I hope you have understood about the structure of ethyl. Okay, now let's proceed with the next one, and that is going to be the reactivity.